Hello folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to calculate both electric fields and electric potential for a one-dimensional charge distribution, and also to talk a little bit about the mathematical relationship between the field and the potential. So what we're looking at here is what I'd like you to imagine is a total charge Q spread out linearly and uniformly over a total length L, as I've shown in this picture. One thing I'd like to comment about is, in most of my examples, I tend to use a lot of positive charges. The problem is identical if this ends up being a negative charge distribution, other than I would put minus signs along this line. And then the only difference would be when I draw the electric field vector over here, it would be left rather than right. Other than that, there's no difference for the electric field calculation. And then the electric potential calculation will be identical, other than you'll get a negative number instead of a positive number. So, there's really no difference. So I tend to usually default to positive charges, but I'll try to throw some negative charge distributions in some of my future examples. But anyway, all right, so what is it we're trying to do here? We want to be able to calculate, what is the electric field at this location, a distance a away from one end? And what about the electric potential? Now you'll notice I put a vector symbol over the field, but not the V for potential. Usually we use this kind of capital letter V for electric potential. Electric potential is an energy concept. It is not related to, I shouldn't say it's not related, but it's not a vector quantity. Electric potential is potential energy per unit charge, right? So it's an energy concept, not a vector. All right, so getting back to the electric field calculation. So first thing we ask ourselves is, how do we find the electric field? Well, one way is this. We know that the electric field is equal to kq over r squared, but this is true for point charges. This is a charge distribution. What I can do, however, is I can break this up into little pieces that are point charges. So you have to imagine breaking this into a little chunk here, and I might give that chunk a length. I'm going to call that dx, which reminds me, since we're dealing with vector quantities, before I've even done this, I probably should have put in a coordinate system. So I'm going to go back and maybe left-hand side here, put a x, y, z would be coming right at me coordinate system. I chose the left end to put that coordinate system, but you don't have to. You could put it in the middle, or you could put it over on the right, or you could put it at point P. You can put the coordinate system anywhere you want. I'm going to go ahead and just stick with the place I put the coordinate system. That makes this distance in my picture equal to x, distance to my chunk of charge. Right? Now what I'm going to do is draw an electric field vector at P. And that field is going to be the field created by this chunk of charge. And because this is positively charged, the electric field vector would point to the right. Right here is where there would be a difference. If this thing were negatively charged, then this field vector would point to the left. Other than that, there's not going to be any other difference in this problem. Okay, now we got to label this. Because this is the electric field, due to a small and infinitely small, because that's a dx, an infinitely small chunk, that makes the electric field actually infinitely small as well. So I'm going to label that dE. Now, I'm going to now use the point charge relationship to write out what this is equal to. K, now let me hold off on the Q for a minute, over r squared. Now the Q is going to be the charge of our chunk, and because the chunk is infinitely small, the charge of that chunk is also infinitely small. So I'm going to call that dq. So this basically is a relationship I'm going to use to find the electric field. We're going to have to figure out something to put for the dq and also the r. The r in this equation is going to be from the chunk, which is here, to the point, which is here. So let me actually just go through and highlight that real quick so we're clear. The r is this distance, which I've done in green. I'm going to get rid of that now. Now, from here to here is L. From here to here is L plus A. So the distance we need, I'm going to do that in blue here, that's going to be this distance is equal to L plus A minus X. Right? So our R is equal to L plus A minus X. So the electric field dE can be written K, I'm going to leave a little room here for the dQ, K dQ over L plus A minus X squared. And now I'm going to talk about the charge, the dQ. Here's an example of where we use a charge density. In this problem, if I take a total charge Q, divide by a total length L, then my linear charge density is Q over L. Therefore, my charge, dQ, is going to equal the charge density, Q over L, times the length of my element, dx. If you look in the textbook, you might see an example like this, where the Q over L is just written with this Greek letter lambda, which means linear charge density. I like to just put the variables of the problem in. So right here we're going to have Q over L dx. So there's my expression for the electric field. This gives just the magnitude. The direction is to the right. All charged components are going to give us a field to the right, so I'm just going to attach a direction at the end of this and just worry about the magnitude for now. All right. Now, total electric field, therefore, we would get by adding these all up. Now, in mathematics, that's what the integral does. So it's going to be the integration of this expression from x equals 0 to x equals L. And this expression's a little kind of long to write out. All right, there we go. So, net electric field is going to be given by this integral. Now, I'm going to go ahead and write it one more time, clean it up a little bit. Anything that's constant, and again, looking here, these are all constants. So we can say that the electric field can be written KQ over L, integral 0 to L of dx over L plus A minus X squared. Now, the rest of the electric field calculation is all math, so I'm going to make myself some room here, get rid of this, and talk about just working the integral here. So if you can work that in your head, that's perfectly fine. I like to do things one step at a time, and I'm going to actually show the steps to work this after I get rid of this. Get out of there. And what I'm going to do is I'm going to do a substitution on this, right? And from calculus class, these are usually called something like U substitutions or something like that. What I'm going to do here is I'm going to let U equal to L plus A minus X. Du would then equal minus dx, keeping in mind that L and A are constant. And, some people like to do this kind of halfway and go back. My advice is this. When you do an algebraic transformation, just transform everything, limits included. And I'm going to go ahead and do that. If x is equal to 0, right, that's my bottom limit, then u is equal to L plus A. And I'm getting that by putting that 0 right there and just observing what u would equal. And then if x is equal to L, then u would equal, now notice if you put an L right here, L minus L is 0, we're left with just A. So what we have now is that our electric field can be written as a new integral. Let's see, KQ over L, integral. Now it was from 0 to L, now it's going to go L plus A to A. And then dx from right here, I can see is equal to minus du. And then L plus A minus X is equal to u. Okay. So we've transformed our integral into a nice easy one. Now, how you handle the minus sign is up to you. I like to handle the minus sign by absorbing these into limits when I see things like this. So this is going to equal, absorbing this minus sign into the limits, the integral a to L plus A du over u squared. And again, if you're not familiar with that, I've got other videos about making integration and limits and things like that, and how to handle that. But that's just coming from absorbing this integral into the limits. Now, this is the integral of du over u squared, so we're going to end up with kq over L. Let's see, antiderivative of u to the minus 2 is minus u to the minus 1. So this is going to integrate to this, evaluated from A to L plus A. Okay. And believe it or not, we can actually absorb this again. Let's see, kq over L. How about we write this 1 over u evaluated from L plus A to A. which is going to be KQ over L times the quantity, 1 over A minus 1 over L plus A. And there's our expression for the electric field. With all the pluses and minus signs floating around, let's just kind of check it for sanity, make sure our sign worked out to the right, correct. I've got the field to the right. This quantity is in fact positive because 1 over A is bigger than 1 over L plus A, guaranteed. So I got a positive value confirming my direction. This looks consistent with what I was expecting. I'm going to go ahead and clean it up just a little bit. KQ over L. Let's see, if we did a common denominator here, I think we're going to end up with L plus A minus A. So that's going to give us just L over A times L plus A. I believe that's right. Oh, and that's kind of nice. These kind of reduce. So what we end up with is KQ times the quantity 1 over A times L plus A. And this is the magnitude of the electric field. The field vector actually points to the right. I'll just put that. It has units of KQ over distance squared. Another check I like to do is just make sure that if A is large compared to L, it should converge to 1 over A squared, because if A is large compared to L, this would look like a point charge. And you'll notice if A is large compared to L, let's see, I can basically just lop that off, and we get KQ over A squared. So this looks right. I'm going to go ahead and pause this, store the results, and then look at what the electric potential calculation looks like. All right, folks, so I'm back. I've gotten, cleaned my page up a little bit. I kind of stored my results here, that the electric field vector at point P here is equal to KQ times the quantity 1 over A times L plus A. Direction is to the right. That's a I hat there for a unit vector. That's why because it has a direction, I can go ahead and put that vector symbol on it now. Now we're going to talk about the electric potential calculation. So for starters, the electric potential due to a point charge can be written KQ over R. So the Q is the same. We already found that. The Q for our point charge here we could call dQ, which is equal to Q over L dx. The R is the same as it is before. The R is distance from the chunk to the point. That's that distance right there. We already know that's equal, L plus A minus X. So we can just start moving forward with the calculation. So we can probably start with this, that the electric potential at P is equal to K dQ over R. This is a differential potential because I'm talking about the field produced only by that infinitely small point charge. I'm sorry, not the field, the potential produced only by that infinitely small point charge. This is a dQ again because, again, my point charge infinitely small. You notice I haven't drawn any vector for that. Well, that's because electric potential is not a vector quantity. The next step here, I guess I'll write it over to the right here. So dV can be written K. Now the dQ, same as it was before, Q over L dx, over R, which is same as it was before. L plus A minus X. Total electric potential, we're going to add these all up from 0 to L. And while I'll just do this right now, these are constant, they can come out in front, KQ over L, and we have just dx over L plus A minus X. I'm going to go ahead and walk through the substitution for this. Many of you probably can integrate this in your head. No doubt we have a logarithmic integral coming, but this is what it looks like if we actually do the substitution. I'm going to let U equal L plus A minus X. Du would equal minus dx. If x is equal to 0, u is equal to L plus A. X equal to L, then u is equal to A, basically same substitution that we had before. That makes this integral identically equal to the following. Let's see, integral L plus A to A, dx is equal to minus du, L plus A minus X is equal to just u. Okay, we can do several things with this constant. I think last time I absorbed the constant here. This time I'll take it out front. Minus KQ over L. I'm going to go ahead and do this right here. Antiderivative of du over u is natural log u, evaluated at these limits, L plus a to a. And like I did before, at this point I'm going to go ahead and just absorb these into the limits. So this is going to be kq over L. Now, I'm going to save myself some writing here to rewrite this. The minus sign will absorb in. That's going to make this the top limit, this the bottom limit. By time we do natural log of this guy minus natural log of this guy, and we apply logarithms, we get natural log of L plus a over a, right? And that, that's just absorbing this into the limits and applying a little bit of rules of logarithms. I'm going to check this. I'm expecting a positive value for the potential. Well, this is obviously positive. Looking right here, you'll notice this is guaranteed to be bigger than 1. Natural log of a number bigger than 1 is in fact bigger than 1, so, or bigger than 0, so that thing is positive. And it's looking right. So I'm going to take a moment here now and clean my page up here and chat a little bit about the relationship between the potential and the field. All right, I'm back, made myself some more room. A couple quick comments here. So these equations I've got on the right, the point of this video is not that these are equations that you need to memorize those, right? In physics, it's not very handy to memorize very little at all. The point of the video is how these are developed from the concept of taking a charge distribution, breaking it up into little pieces that are point charges, and then applying point charge relationship for an electric field and for electric potential, and then using mathematics to develop those into electric field and potential equations for the charge distribution. So the concept of how this is done is what's important, not memorizing these equations. I do want to take a moment, though, and look at a piece of mathematics here. So the potential is equal to this expression, and what I want to do here is this variable here, if that variable increases by an amount dA, or by a small amount, an infinitely small amount dA, the potential is going to change. And what I want to do here is just calculate dV dA from this expression right here. And the kq over L constant, when you differentiate a natural log function, you get 1 over, the derivative of ln u is 1 over u du. So this thing's derivative is going to be 1 over this animal, which can be actually written like this. I'm going to go ahead and flip that upside down. There's the 1 over u part times du, meaning differentiating this by chain rule. So when we go ahead and differentiate this, the derivative of the top, 1 times the bottom, keep in mind we're differentiating with respect to a, minus the derivative of the bottom times the top, all over the bottom squared. So hopefully I've done that right. That's the derivative dV dA, differentiating with respect to a. I'm going to simplify this down a little bit. So we get kq over L. Now you'll notice we've got an a up top, 2 in the bottom. That's going to get rid of those. Kind of inspecting that top, here's an a minus another a. That's going to be gone, but this term looks like it's going to survive for now. Minus L up top. Bottom, we've got one of these a's and a L plus a. And you'll notice that the L's divide out and we get minus, that minus sign does stay, kq over a times L plus a. And what I want you to do is kind of stare at that. We're going to look at that. And I want you to stare at, let me highlight it here. We'll do this here, blue. Take a look at this. Take a look at this. And you'll notice those are the same thing, except the minus sign. Well, the minus sign is coming from this. Well, let me back up. This suggests a relationship, a mathematical relationship between the field and the potential, and there is. The electric field, and let me just talk magnitudes for a minute, is in magnitude equal to dV d. I'm just going to say dr for now, where r can really be any direction. And you'll notice that if I take this and if I take my electric field electric potential, differentiate it with respect to position, I get the electric field out of it. That's exactly what we just did. I took the potential, differentiated with respect to change in position, and out came an expression for that's the same as the electric field. The minus sign is occurring because of this. Or let me try to make it make physical sense. If this is a first derivative, if I write this dv equals E times dr, for now not worrying about vectors and directions and things like that. If your dr is positive, we're moving away from the field. The potential is decreasing. As we move away from this charge, we should be moving towards lower and lower and lower potential. That's why the minus sign here, this gives the correct mathematical relationship between the electric field and the electric potential. And this is what this is, that the electric field is equal to the derivative of the electric potential with a minus sign. Basically, it's minus dv dr. The r is whatever variable you're differentiating with respect to, or I should say whatever position variable. You might differentiate with respect to x, you might differentiate with respect to y, you might differentiate with respect to some outward type of variable like r, but for now, the purpose of this video is not to deeply go into that mathematics, just to demonstrate for you that there is a derivative relationship between the electric potential and the electric field. Basically, when you differentiate the potential, you get the electric field. That's important for a couple of reasons, not the least of which is, it gives you a second way to find the electric fields. You'll notice that some of these problems can get kind of complex. It can be very difficult sometimes to work through the integration. Well, the electric potential may have an easier integral, and then we know that we can just differentiate our results to get information about the electric field, that kind of thing. Again, the purpose not to talk a ton about this. I'm going to make a completely separate video about the relationship between the field and the potential. Purpose of this video was how to break a linear charge distribution like this up into point charges like this and apply these relationships to find expressions for the electric field and electric potential. Those were the main features of this video. But I just thought I would tack on a little extra here that you talk about that these two things are related via a differential relationship, or a derivative relationship. Anyway, this video is probably plenty long. Hope you had a great day, and watch for more fun.